overcoming the lack of NWI information in North Mississippi. In our investigation of efficient methods to provide early assessment to wetlands potentially impacted by transportation corridors, we adopted existing findings of woody wetlands in North Mississippi. According to Brooks et al., 2009, the motivation in improved methods of mapping forested, or woody, wetlands areas was twofold: National Wetlands Inventory, NWI. Digital mapping information of wetlands location is unavailable for approximately 1/4 of the lower 48 U.S. states, including Northwest Mississippi, based on the U.S. Fish and Wildlife Service NWI Wetlands Online Mapper, and forested wetlands are very poorly mapped using traditional mapping methods including optical remote sensing, Sater et al., 1995, Borgo-Chavez et al., 2001. Availability of national wetland data, modified from U.S. Fish and Wildlife Service, National Wetland Inventory, background image source, Google Earth. Given this data gap and problems with available traditional sources, we adopted the results described by Brooks et al., 2009, that used a combination of radar remote sensing data with object-based techniques to compute potential woody wetlands and create a soil moisture index map for the NCRSD SEP project. The top-down watershed-based landscape analysis. The partition of the landscape into hydrological watersheds was a logical ecologically focused way to explore the context interactions between the natural and the man-made features. The methodology employed concepts of object-based geographical analysis to evaluate the level of landscape impact of the proposed transportation corridor scenarios. The focus on hydrological watersheds as principal objects made the main difference in comparison with the traditional object-oriented landscape analysis. 2 levels of hierarchy were addressed in this work. Watersheds were identified and ranked according certain criteria as a significant percentage of unfavorable zoning, density of streams, wetlands and future man-made constructions. Wetlands identified and ranked for each watershed. This used topographical LIDAR data, image interpretation and the wetlands impacted by the designed I-269 corridor. Potential woody wetlands product for the NCRSD SEP I-269 study area. An I-269 area GIS was developed to improve the capabilities of geographical analysis by providing ways to access, process, store and disseminate large amounts of information in comparison with human tasks. The traditional GIS features, points, lines and polygons, enable a series of spatial operations as union, overlapping, intersection, etc. Some of these operations were used when integrating the watershed polygons and the landscape layers of information on the first level and when assessing and refining wetlands on the second level. The first step was the identification of the HUC 12 watersheds intersected by the part of the I-269 bypass that included alternative routes in the southeast part of the area located in northwest Mississippi. A simple spatial intersection operation highlighted 10 watersheds as shown in. Selecting the watersheds intersected by the I-269 corridor options area caused a significant reduction in the field study area and, consequently, the optimization of the data to be processed. Thus, the next step assessed the numerical criteria that enabled ranking the selected watersheds. At this point, the polygons of the 10 selected watersheds were intersected with other layers of information such as 100-year floodplain, hydrograph, existing roads and urban features, planed roads and developments and zoning in order to extract features to quantify the system. Illustrates the layers used in this intersection. The basic workflow for the 2 levels of the hierarchical process. The HUC 12 watersheds intersected by the Part 1-269 analyzed in Desoto County MS, which was the section with corridor options assessed as part of the ICE. In order to make straightforward the process, the zoning map in particular was previously reorganized into 5 classes: agriculture, green, residential, yellow, agriculture residential, light green, commercial, red, and industrial, orange. Similarly, the maps of existing roads and existing buildings provided by Desoto County GIS Department were combined to produce a density map that reflects the urbanized areas. These steps were necessary since no map of this kind was found to be available in existing GIS databases. Spatial intersections between the selected wetlands and the layers of interest to assess watershed characteristics to be used in the MCDM process. Aiming to simplify the decision-making process, quite a few different impact factors were assigned to the layers of interest, ranging from 1, low impact, to 9, high impact. These values were hypothetical, but reflected the importance of the features due to the potential environmental impact upon existing wetlands. The percentage of covered areas was computed per watershed for the following GIS layers: watersheds, 100-year floodplain, dense urban, future developments, residential, agriculture, agriculture residential, commercial and industrial. Similarly, the density of linear features, km per km2, was computed per watershed for the layers perennial streams, intermittent streams and planned roads. Table 1 presents the relative values extracted per layer from the selected watersheds. These numbers were used to compute the ranking through the weighted average, as shown in the equation 1. Relative values computed per layer per watershed, percentage of area and density of linear features. Unlike the federal and small-scale geodata, local, large-scale or ground-level geodata normally demand substantial time to be computed due to the high resolution and accuracy involved. Aerial images, high-resolution satellite images and LiDAR are the most data-intensive information in GIS in terms of storage and interpretation requirements. Minimizing computational efforts by analyzing the landscape, subdividing the geography into semi-homogeneous units, selecting units for further detailed analysis, and prioritizing areas of interest is key to reducing the geographic extent of the study, reducing the computational cost of the study, and supporting the top-down approach in geospatial analysis, in which the analysis funnels options down into a reduced set of possible alternatives. Given the completion of level I processing described, a series of GIS analyses using information extracted from the topographic surface, such as topographic depressions and flat areas, as well as image analysis such as land cover, provided enhanced inputs to refine wetlands feature geometry as well as classifications based on the radar-based wetland mapping results. The following processes were developed for the watershed number 0, which is second in the ranking as shown in the results section. It serves as a representative example for more detailed examination in this lecture. The reason is that the top-ranked watershed covers a small area and is mostly composed by developed areas and does not present a large variety of landscape features, including wetlands, to illustrate the exercise proposed in this work. The geospatial analysis was performed using map algebra, so features in vector formats were converted to raster format. Due to landscape analysis considerations and the potential implications of I-269 and planned roads, the layers of information selected in this level, Level 2, emphasize the hydrographic and physical aspects, which are basis for engineering construction perspectives. The layers employed to refine and rank the wetlands per watershed. For display purposes, the impact factor ranges from green, low, to red, high. Table 2 presents the layers used to refine the wetlands features, their respective criteria for classification and the weight to be used on MCDM. Distance criteria and weights are hypothetical, however, they reflect the goal of the paper on assessing potential impacted wetlands. Layers, criteria and weights used on Level 2 analysis. The weights are included in the multi-criteria decision tool as input rankings. The tool was developed as part of the CEP in CRST project and implemented based on Saudi's HB method. The normalized weights are used as factors in the map algebra equation that is responsible to produce the cumulative cost surface, where high cost would represent higher environmental impact,